I'm very happy to be here. I've been in Beijing at Tsinghua before, but never before in BIMSA, the institute, so it's very impressive. Okay, so this is a colloquium talk. It's not meant for specialists, and I don't know what you should be a specialist in anyway. It's a very elementary subject. So I want to talk about partitions. The title, I think you didn't say the title of the talk, but the title I gave was The Power of Partitions and Partitions into Powers. So I'll just put power and partitions. So partitions, I think most people, most mathematicians in any field have seen them. A partition of for instance, 5 is, well, I can list them. It's a partition of a number is a decomposition into positive pieces where the order doesn't matter, so it's just the possibility. So there are 5 possibilities. If you have 5 objects, you can divide it into 5 sets of 1 object, or into 3 sets of 1 object and 1 set with 2 objects, or 1 plus 1 plus 3, or 1 plus 2 plus 2, or 1 plus 4, or 2 plus 3, or 5. So there are 7 of them, and then we write that the number of partitions, so this is the partition function, the number of partitions of 5 is 7, because here they are. So they have a very old history. They're very important in every part of mathematics, also of mathematical physics. And I want to mention this talk some of the important things from the past, and then a kind of a news story. So it's a paper that I wrote, came out only 2 years ago, when you replace this ordinary partitions by partitions of the number into squares or into higher powers. But I want to begin with the usual one. So there are 3 main things in the history. One is Euler, one is Dedekind, but it's really Dedekind and Riemann. And one is Hardy and Ramanujan. And that work was later refined a little bit, but it's a very nice theorem, but the big breakthrough was the invention of the circle method, essentially by Hardy and Ramanujan, and they formed it. So I want to tell these 3 classical things and then something else. So this is 18th century, this is 19th century, this is 20th century earlier, and then Oliver's story about power partitions, which is 3 years old. So the 4 parts are from 4 different centuries. So let me start with Euler. So Euler invented this number. He thought of counting the number of partitions. And in that context, he introduced one of the most important things that we have in all of mathematics, which is the concept of a generating function. So if you want to understand this number, the obvious way is just to make a table. So n, p of n, so 1 is 1 partition, 2 has 2, 3 has 3, 4 has 5, 5 I just did is 7, 7 has 11, 6, 7 is 15. And of course these numbers, and by the way, you should always include 1, the 0 case in any theorem. So the number of partitions of 0 is 1. The only way, there's one way to write 0 as a partition, namely the empty set, but it's unique, so it's 1. But if you continue, then when you get to 200, I used to know this number by heart, but I forgot it's 39729990029, 388. So this number, by the way, was computed by hand, but only in the 20th century. I'll come back to that later. But Euler invented these numbers, and he computed the first few, but he wanted to know how to compute them. And so he invented the notion of a generating function, which today we all know, and he invented, I think, for exactly this case. So this is all Euler, what I'm telling. He said that if you have a sequence of numbers, instead of making a table, the intelligent way to do it is to make a function. I'll call it capital P of x. Actually, I'll call it capital P of Q. Usually it's X, but I prefer Q. So you simply use these numbers as the coefficients of a power series. And so what he noticed, so that was already extremely important for the development of mathematics, is to even have the idea of making a power series. But the reason of making a generating function, the reason generating functions are useful is because you can transform the properties of the numbers into properties of the function, and obviously that's much clearer. So what he showed is that this has an expansion as an infinite product, so it's much simpler. Here, these numbers, we don't know what they are. Nobody knows what this is. But this is just 1 over 1 minus q, 1 minus q squared, 1 minus q cubed, etc. And so you have something you can understand much better. And maybe I'll recall the proof. So the right-hand side, so this is the proof. The right-hand side of this equation is if I expand 1 over 1 minus q, q is small, less than 1 or small, so it's a geometric series. Then I'll have multiples of q squared and powers of q squared, so multiples of 2. Then I have powers of q cubed, so multiples of 3, etc. So if I call this q to the a, then a is greater than or equal to 0. But this is q to the 2b, and this is q to the 3c, etc. So a, b, c, etc., all greater than or equal to 0. And you see that if I look at the coefficient of q to the n, it exactly tells me I write n as a sum of a1s, b2s, c3s, and so on. So it's a partition. So the proof is very easy. And in this way, we already have a very nice structure. Then the next thing that Euler did is he said, this function looks a little strange because it's 1 over something. Unfortunately, this thing doesn't go down low enough, and I'm very short. So I don't think I can use, I can sort of get there. So Euler said, why should we take the reciprocal? The natural function here is this one. So this would be P of Q inverse. And so he said, if we could understand this function, then we could also take 1 over it. We could understand the whole function. So he multiplied this out by hand. Of course, there were no computers. And when you do this, what he discovered, he went up to q to the 50. This is a good lesson for us today. Nobody computes. They ask their telephone to their computer. But if you compute by hand, as people used to do, you learn many things. And Euler always computed very far. So he went up to, well, of course, now we can go much further, but he went up to the 50 terms. And he saw that every coefficient in this expansion, most of them were 0, like the coefficient of q to the 11 is simply 0. But all coefficients 0 or plus or minus 1. And if you look, you quickly find the rule. This is the sum, k, an integer alternating sum of q to the power 3k squared plus k over 2. So that was Euler's beautiful formula. And then if you compare this thing, then this tells you that since P of Q times P of Q inverse is 1, the nth coefficient, when the coefficient of q to the n in 1 is simply 0 for n positive, so you immediately get that 0 is equal to P of n minus P of n minus 1 minus P of n minus 2 plus P of n minus 5 plus P of n minus 7 minus etc. So from this expansion, you immediately get a recursion. And so if I know P of n prime for n prime less than n, I get P of n. And they're only approximately constant times square root of n terms. So if n is not very big, you can compute. So using this, Euler computed up to, I don't know, 30 or 50. So this was one of the first, I think it was the first use of a generating function in mathematics. So that's what I wanted to say about Euler. But then Dedekind found that this same function if I change it very slightly, it turns out you should multiply by q to the 1/24th. So in other words, this is, well, then you find something very nice. And so Euler didn't think of this. We know now that why we should do this. It has to do with modular functions, I'll say in a minute. But actually from Euler's form, you can see that this is a very good thing to do. Because if you take Euler's formula, here you have a quadratic form, but in mathematics, you often have theta series, and the theta series is always q to a power which is a quadratic form. But this is not a quadratic form, it's a quadratic function. It is a linear part, and so we should complete the square like you learn in high school. So 3k squared plus k over 2, you can write as 1/24th of 36k squared plus 12k, which if you add 1/24th, it becomes 6k plus 1 squared. So here I could also call, once I multiply by q to the 24th, this becomes 6k plus 1 squared over 24, which is kind of not a very good way to write it, but so this is simply the sum n in z, but n congruent to 1 mod 6, minus 1 to the n minus 1 over 6, q to the n squared over 24. So Euler's formula tells us that you should multiply p of q by q to the minus 1 over 24. And you should multiply its inverse by this. And this function now has a name. It's called eta, and it's called the Dedekind eta function. But like many names in mathematics, it's not the correct name because Dedekind didn't discover it. It was actually discovered by Riemann. And in fact, Dedekind's paper is called, well, it's in German, but it says on a fragment of Riemann. So Riemann died young in 1866, he was 40. And if I remember my history right, he never married, but he lived, I think, with his sisters. Anyway, he had sisters who asked Dedekind then to go through his papers after he died and find out if there were interesting things that he had never finished or been able to publish. And Dedekind found one fragment, it was incomplete, so the paper is called On a Fragment, on an incomplete work of Riemann. And Riemann had found this function given its main properties, and Dedekind worked it all out. So that's the eta of eta function. But here the variable is not q, it's eta of tau. So tau will be a complex number. With positive imaginary part. So that's imaginary part. So this is h, that's a German h. If you don't know, so if you draw a picture, it's just the upper half of the complex plane. So it's called the upper half plane. And q is e to the 2 pi I tau. So this eta of tau I can also write as e to the pi I tau over 24, over 12, sorry, the 2 pi. And then minus q to the 25 pi I tau over 12. So as I just showed you, all of the terms will always be q to the 1/24 times the perfect square of a number which is prime to 6. So you get this nice formula. And the reason, so this is the Dedekind eta function. And what Dedekind proved, but I think Riemann already knew, is that you have this marvelous functional equation. So the theorem, so this is the exciting part, but there's also a trivial part, easy or obvious, which says that eta also has a second transformation equation. If you replace tau by tau plus 1, so in the upper half plane, if you take 1 over tau, it's in the lower half plane, but minus 1 over tau is in the upper. So this is legitimate, but you can also send tau to tau plus 1. So we have two transformations, minus 1 over tau and tau plus 1. And so eta of tau plus 1, if you send tau to tau plus 1, q doesn't change. because q is simply e to the 2 pi tau, and e to the 2 pi I is 1, also Euler. But of course, we also have this q to the 1/24th, so we'll actually multiply the function by a constant, whereas a to n, I'll use the notation later, simply means e to the 2 pi I over n. So this is a root of unity. It's kind of the standard root of unity, nth root of unity. So we have these two transformation laws, and the reason that this is very important there's no place to put this. Maybe I'll bring this chair closer. So the two transformations that I just wrote tau goes to -1 over tau, and tau goes to tau plus 1, generate the group, the modular group, so this is the group, it's called usually SL2Z, so 2 by 2 matrices of integers with determinant 1. None of this will be used in the rest of the lecture, but it's kind of very important background, so I wanted to give it. And this acts by tau. So for any such matrix, you have a transformation which sends tau to A tau plus B over C tau plus D. This is a group, and to understand the group, you only need the generators, and these two special elements are just two special generators of this group. So this group is generated by these two matrices. So this is therefore one of the first, I don't know if it's the very first, but one of the first examples of a huge field of mathematics, which is my favorite field and my specialty, which is the field of modular forms. So this is a modular form. A modular form in general is any function which transforms under -1 over tau and tau plus 1, or equivalently under all transformations like this, but in general with some factor, like this factor here. So that was the second thing in my list of important properties. So first, partitions gave us these beautiful identities of Ramanujan, two identities. One, that the generating function of Pn is a product expansion. The second was that this sum was so Euler's two beautiful identities, and the invention of generating functions. That was my 18th century example. My 19th century is that Dedekind, or Riemann and Dedekind, discovered that you have this Dedekind eta-function, which is very important, and there are, many, and the theory of modular forms has become now one of the key parts of all of number theory and a lot of other mathematics. So the third thing that I had on my list was Hardy and Ramanujan. So I gave you the value of P of 200, and you see it's a very big number. So we would like to know how P of n grows. So as n goes to infinity, we would like to know the rough growth of P of n. And so it turns out the most primitive theorem is actually relatively easy. So the log of P of n grows like a constant times the square root of n. And the constant is pi times the square root of 2/3. This is relatively easy. But there's actually a much more precise formula. And so first I can give some examples. P of 200 I gave. I don't want to bring that board down. I'll give some more examples. P of 1,000 is approximately 2.4 times 10 to the 31. P of 200 I already gave you. It's approximately 4.0 times 10 to the 12. And P of 5,000, I mean, you can compute these numbers very quickly on a modern computer in a split second. But they grow very fast. So P of 5,000 already has 75 digits. So you want to know how it grows. And as I said, it grows exponentially, but not exponentially in n, but exponentially in the square root of n. But there's a much more precise formula. So now I'll tell the Hardy Ramanujan formula. So first, let me define an elementary function. E of x is 1 over x squared minus 1 over x cubed times e to the x. So it's roughly just the exponential function, but slightly modified. So e for exponential. And now the formula for p of n, but it's an approximate formula. I'm going to write an infinite series which actually diverges. You have to truncate. You have to take only a finite number of terms, but very few terms are enough. So there's a prefactor, pi squared over 6 squared of 3. And then you take e of pi times the square root of 2/3, but it's not n, it's n minus the 24th. And the reason for that is we already saw that the natural coefficient is not for p of q. The p of n is not really the coefficient of q to the n because this is the natural function. It's really n minus the 24th. So here, the leading term is that. And already, if I subtract this, so if I just subtract p of n minus this first term, I'll just put one term, then this is roughly the square root of p of n. So if I do it for 5,000, this number has 75 digits. But if I write just this first term that I wrote, then the first 37 digits will be the same. So the approximation is not just asymptotic for the first 2 or 3 digits, it's the first half of the digits. The next term is much smaller, it's like the square root of the main term. But in fact, I can be much more precise. The next term is alternating. If n is even, it's plus, and if n is odd, it's minus. Plus or minus 1 over 2 squared root of 2. And then it's exactly the same argument as before, but it's half. So since this is exponentially big, this is e to the x for some big x, roughly square root of n. This is like e to the x, this is like e to the x over 2. So if this is 74 digits, that is half as many digits. And then the next term, and all of the terms, the next term will be, instead of minus 1 to the m, is something of period 3 times, and then you just take the same number exactly, but you divide by 3. So the kth term in this approximate is roughly the kth root of the leading term. So since these numbers are very big, the first term is 1,000 digits, the next is 500 digits, then 333 digits, then 250. So therefore, this is extremely accurate. And I'll give you an example. This infinite series diverges. You can prove that. But you stop after a certain number of terms, and they proved in their paper something amazing. This form is totally amazing. They proved if you stop after the right number of terms, and they've showed it's roughly the 4th root of n terms, then these numbers are huge, but the error is not only much smaller than the main term, but the error actually goes to 0. And so you get something which is very, very close to the answer, but the answer is an integer. So if you do that, you just round off to the nearest integer. So although it started as an asymptotic form, it's actually exact. So let me give you, for n equals 200, I'll give you the first 5 terms. So here we have k is 1, 2, 3, and then 5. So k and the term, I'll just put k equals 1. It's 3, 9, 7, 2, 9, 9, 8. So this first term, this one. 3, 9, 7, 2, 9, 9, 8, 9, 9, 3, 185.196. The next term is already much, much smaller. It's only 36,000. So you see already at the beginning, that's what I meant. It's such, you get 3, 9, 7, 2, 9, 9, 9 already just from the first term. The next term is already down to only 36,000. The next term is only 87.555. Sorry, you can't read this. The next term is plus 5.147. The next term is plus 1.424. So they're getting very small. If I add this up, what I'll get is the error is now something like 0.2. So we get the exact integer with only 5 terms. So many of you have seen this, certainly the number theorists have seen this. It's never written quite like this. You've probably never seen it written exactly in this form. But this is one of the most amazing formulas, certainly in mathematics, that you can give a number which is an exact integer as the truncation of a sum of terms of very different orders of magnitude. But when you add them all up, a very small number of them, actually you need much less than the fourth root of n terms, then you actually find the exact value. So that's certainly a very nice fact. So that's the background of what I want to tell. And I want to now pass to my next problem, which is the subject of the lecture. So, by the way, I didn't say when they did this is over 100 years old, 1918. That's when Ramanujan went back to India. So maybe many of you know the stories. Ramanujan had a very bad job as just an administrative job as a clerk in Madras. In India, he wrote to Hardy, who invited him to come to England, but actually he wrote to many mathematicians, and everybody just threw away his letter because it looked crazy. But Hardy took it seriously. He discussed it with Littlewood. They invited him and had this wonderful collaboration. But Ramanujan very much wanted to go back home, but he couldn't because it was the war and there were no ships. I mean, it was dangerous. So he had to stay in England till 1918, and that's when they published this paper. Then he went back, and unfortunately, he died 2 years later. He died in 1920. So that's the story of part of the power of partitions that we have this. And by the way, Ramanujan, since I mentioned him, did many things with partitions. And one of them he discovered, and he proved, that if you take any m, which is 4 mod 5, so we had the p of, remember p of 4 was 5, maybe you don't remember, but it's still in the table. So p of 4 was 5, but p of any number which is 4 mod 5 is always divisible by 5. And similarly, p of 7k plus, I can't remember, I'll have to look. I think it's 7k plus 5 and 11k plus 6. I don't quite remember, but anyway, with some shift, you get congruences modulo 5, 7, and 11. And by the way, no other prime works. It's only for these 3 primes. And he gave proofs of this, but complicated. There are many proofs now, and actually recently I gave a very, very simple proof, which I think is already came out, and it uses exactly this generating function, used the Dedekind eta function in some theory of modular forms. So this is just a sideline, a very beautiful fact. I'm not sure if this is the right number, but the right thing is that if L is 5, 7, or 11, and if, remember, it's not n that counts, it's n minus the 24th, this should be divisible by L. Then P of n is also 0 mod L. So you can say this isn't an integer, but it's prime to L. So you could also say 24n minus 1 is divisible by L. So then you see 24 times 4 is 96, minus 1 is 95. I don't know if I got them right, but I think they're correct. Okay, so these functions have amazing properties, but I want especially to tell the asymptotic formula and the Hardy-Ramanujan formula. So now I want to say my subject, which is partitions into squares. So I'll mostly talk about, right, the formula is just for squares, so it's not for p or higher powers. It's the same. So you could also partition into cubes and so on. So I now define P2 of n. So P of n was the number of partitions. This is the number of partitions of n. So you break it up into positive numbers, but they aren't arbitrary numbers. They're perfect squares. So for instance, I don't know if I have a convenient example written here. Okay, let's say P of 10. P2 of 10, for instance, will be 4, because you have the only ways to write 10 is the sum of squares. So if you start with 9, then you only have 1 left. You can't have any bigger squares. 16, there's no room in 10. If you don't start with 9, you can put a 4. And then we have 6 left, so I could put 6 ones. Or I could have a 4 and put another 4. And then I have 2 ones. Or I could put just 10 ones. I don't want to write them all out. So there are exactly 10, only 4 partitions, but of course there are many more partitions. So P2 of n will be much smaller than n. So this was actually already introduced in the original paper of Hardy and Ramanujan. They discussed this, but much more briefly, and they stated some weaker theorems on it. Actually, later at the very end of the paper, and I didn't see it when I published my paper till the very end, they published something stronger, which overlaps with one of the theorems I'll tell, but it's still a bit weaker. But in the introduction, they gave a weak theorem. So remember, for P of n, I gave a very simple theorem that the log of P of n was asymptotic to a constant, specific constant pi squared of 2/3 times n to the 1/2. So for any, of course, you can do this for any PS. I think it's obvious. PS, maybe I'll say that first and then come to this. PS of n is partitions into s partitions into s powers. And then capital PS of Q will be the direct sum, the generating function of these, so we follow Euler. And exactly the same proof that he gave will show that this has a product expansion, but now it will be 1 over 1 minus Q. Well, I'll just do it for P2. But you can put any power, because then I can be more explicit. Instead of 1 minus Q squared, 1 less Q cubed, etc., I take only the squares. Well, sorry, if I write it like this, it's simply 1 minus Q to the n squared. Sorry. And of course, you can do it with any s. It's obviously the same. So we have the generating function, but of course, this will not be a modular form. It will not have transformation properties like this. And so the interesting question is what replaces this? And the natural thing to expect would be nothing. You simply won't have, there is no modularity. This theorem will simply not work if s is bigger than 2. And what I discovered, but much later I found on page 80 of their paper, they come back to the introduction and they say something which is actually equivalent to the theorem I'm about to write, at least a special case of it. So it's actually not quite my theorem. They don't give the proof, to be honest, but they say you can prove that. But I found it numerically. I'll tell the story in a minute. So the question is, what can you say about this? So in the case of log P of n, it was a constant times square root of n. And the statement which they proved is that for every n, it's always a constant. Of course, which constant depends on s, and then a power of s. And instead of the square root, the next time will be the cube root. So for P2, it would be C2 times n to the 1/3, and so on. So it always looks, so this is the relatively easy thing as n goes to infinity. And the CS, I can tell them, they give exactly the value. So CS is s plus 1 times the product 1 over s, gamma of 1 plus 1 over s. Then the Riemann zeta function, which is actually Euler, at 1 plus 1 over s, and that whole thing to the power s over s plus 1. So it's a slightly complicated form, but very explicit. So CS is a known constant. In general, we don't know. So if s is 2, this would be zeta of 3/2. And we don't know zeta of 3/2 in closed form. We happen to know zeta of 2 in closed form, also Euler. It's pi squared over 6. And so C2 is completely explicit. It's pi times the square root of 2/3. Okay? And so I want to introduce this function, but I also want a higher version of the eta function. And so that will be ps of e to the 2 pi I tau as before, but inverse. But remember, before we had to insert the function q to the 1/24th, and it turns out it's very easy to convince yourself that there's only one good thing to put there. It's minus a half of the value of the Riemann zeta function, actually Euler, at 1 minus s. So if s is 1, zeta of minus 1, I mean, Euler already found that there's a way to define zeta of s also to the left of 1, and it's minus a 12th. If s is 2, zeta of minus 2 is 0, so you wouldn't have that correction, but zeta of minus 3 is 1 over 120. And then zeta of minus 4 is 0 again. So in general, you might have a rational power of q in front. So these are the two functions we want to study. So each of them has a product expansion. So this is q to this power times the product 1 minus q to the n to the s without the inverse. So this is the function we want because its coefficients are the number of partitions. And this is the one that might have nice properties. And so, as I told you, eta of tau has this very good transformation property, which is maybe the first example, the first proved example of a modular form. I'm not sure if it was the first. So what replaces that? If we take partitions into squares. So as I said, in the case of squares, this number isn't here, so maybe I'll write it, since we're mostly s will be 2, so eta 2 of tau. There's no power of q because eta minus 2 is 0. So it's simply the infinite product, 1 minus q times 1 minus q to the 4th times 1 minus q to the 9th, etc., where q, again, is e to the 2 pi I tau. So if tau is in the upper half plane, that means the imaginary part of tau is positive, then the real part of 2 pi I tau is negative, and therefore the absolute value of this will be less than 1. So all of our series will converge very nicely. Okay, so eta of 2 is not modular. So it does not set, of course, it has a trivial equation. The second equation, of course, always true. It's always invariant under shift by 1 because it's a power series in Q, and Q doesn't change. If it were eta 3, then you would again have a root of unity because eta of minus 3 is not 0, it's 1 over 120. But apart from that root of unity, the translation part is always trivial. But it's not modular, so no functional equation, FE means functional equation relating eta 2 of tau and eta 2 of minus 1 over tau. But very surprising, that's what I found. And as I said, I found that in some sense, some part of this was given, or something equivalent was stated in their paper. So if I look at eta 2 and then I'll do eta s. So we already know what happens under tau plus 1, so I only want to know what happens here. So here there was a factor, tau over I, and here it's the same except it's 2 pi times tau over I. That part is okay. But then instead of eta of tau, you get a different function, which is eta a half. But eta half is a perfectly good function. Remember, the definition of eta s is q to the minus a half times zeta of 1 minus s. So if s is a half, it's zeta of a half. If s is an integer, as it was before, then zeta of minus s is a rational number. This is some presumably transcendental number. I think nobody knows. But still, it's a perfectly good function. And now it's the infinite product, q, but instead of taking 1, 2, 3 like we did originally, or 1, 4, 9 like we did, now we take the square roots of numbers. But it's still a perfectly good function. It's not at all arithmetic. It does not have an expansion as a power series in Q, but it's a perfectly good function, right? You could say, if you're very picky, Q to the square root of 2 is not well defined, because to take a non-integer power of a complex number, you have to take a log, multiply by that power, and exponentiate. But here we already have a log. So when I write, for instance, Q to the square root of 2, by definition, I mean that you simply multiply tau by the square root of 2 and then exponentiate. So that it's a perfectly well-defined function. And so the story is, but now the argument is not tau, it's the square root of tau. And what's more, the formula isn't finished. There's a second term, which is I squared of tau. So it's a very surprising formula. I was completely amazed when I saw this. So tau, again, is in the upper half plane. So if I take the square root of tau, it's here 0, here's 0. So this is the imaginary action. The square root of tau is in the right half of the right half plane. But that's contained in the right half plane. But now if I multiply by 90, if I turn this by 9 degrees, I multiply by I, then I have the other half of the upper half plane, I squared of tau. So these two things together are both in the upper half plane. They fill up the upper half plane. And then you have to take both of them. And more generally, it works for any s It's exactly the same. So here we had square root of tau over I. Here we had square root of tau over I times 2 square root of 2 pi. So in general, it will be s minus 1 over 2 times the square root of tau over I. And then it's simply the product over all z in the upper half plane. So here, if I call this z and I call that z, then z squared is tau, and here z squared is minus tau. So in general, I take all numbers such that z to the s is either tau or minus tau. So I take all s roots of tau or minus tau. That's two numbers. Each number has s roots. That's 2s, but they come in pairs. Half of them are in the upper half plane, half are in the lower half plane. So there will always be s factors. Here, s was 2, and there were 2 factors. And here, it's exactly what you would now think. You take the product of eta of 1 over s, eta of z, but with index 1 over s. So it's a very strange kind of duality. S goes to 1 over s, but it's not a functional equation for the function a to s. It relates it to a different function, a to 1 over s, but at many points. So that's kind of the main result. Now, I don't know at all how I'm doing on time. I wanted to tell you many things, and I already know it won't work. So I started at 5. It's already 5:45. I've done about a quarter of what I wanted to tell. So there's a very interesting numerical part, how you guess this formula, but I don't want to go into it because I've taken too long to tell this part, and so I won't be able to do it. But the modularity, if you look in the upper half plane, you have one direction. You can go off to infinity by going up. So as the imaginary part of tau goes to infinity, q tends to 0. So if I think of the q, remember q was if tau is in the upper half plane, then q, which is e to the 2 pi I tau, is in the unit disk. So this point will correspond to q equals 0. That's the original expansion that we started, p of n, q to the n. But now, if you know that you have this transformation property, and also here, you can, as tau goes to infinity, 1 over tau goes to 0. So you can also look what happens as tau goes down to 0. Or 1, but remember, under translation, it's the same function, so it's not interesting. If you've done 0, you already know what happens at 1 and minus 1. So now so here q would be 0. I've already written q goes to 0, but here q will tend to 1, which is the first root of unity. But you can also let tau go to the point 1/2 or minus 1/2. Well, they're the same because of the periodicity. But you can also go to 1/3 and 2/3 and so on. You can go to any rational point. And so if tau goes to 1/2, q will tend to minus 1. If tau goes to 1/3, it'll be 1/3 root of unity. If it's a quarter, it'll be I and minus I. So in other words, if tau tends to a rational number, then q will tend to e to the 2 pi I kappa, which is some root of unity. And all rational numbers, every rational number, you can write as a over c. Any rational number where a and c are co-prime. But that's the same as the limit. If you have two numbers that are co-prime, you can find other numbers, d and b, such that the determinant is 1. And so you can think of this as a modular transformation law as tau goes to infinity. So instead of just going up to infinity, using the modular transformation, you can go to any rational point. And so that immediately implies that eta of kappa plus I epsilon, well, I'll write it in a nicer way, I over t as t goes to infinity. So this is a fixed rational number, that there will always be a formula which will be, well, you have to use a factor t to the minus 1/2. This will always be a sum so using the modular transformation equation of eta, you can find that if you approach a rational number, so k plus I epsilon, but for convenience I call the epsilon 1 over t, and then there's a factor squared of t, then it's a sum of pure exponentials. So they exactly correspond to the terms of this thing. This q, remember, was an exponential. It's e to the 2 pi tau. This would be some other exponentials. So it turns out that the same is true for any s. So the other main theorem is if s is now arbitrary, instead of minus a half, it's minus s over 2. That's a detail. We take this new function. Cap is still any rational number, and t goes to infinity. And now it turns out to make the formula look nice, you should write the epsilon as 1 over t to the s instead of just 1 over t. And this will always be a convergent, of course, infinite sum of pure exponentials in t. So in other words, it will always look like this. I could call this AI. It looks maybe a little more natural. So we have certain exponents, lambda I. And so the part that I was going to tell in detail, but the time is too short, you can ask a little is how we recognize these things in practice. So for the first case, it follows from this theorem, but actually I didn't know the theorem when I did this. I first did these experiments and found the expansion, and that led to a statement which said that this identity, the identity of this theorem, was true to all orders. So every term in the sum of the exponentials agreed. These exponentials are negative exponentials. And most of them are going to minus infinity. So this thing is convergent very fast. It's a convergent sum of exponentials. And numerically, you can find this by a very good procedure. So you find the first one, the first lambda 1, the first coefficient a1, then we subtract it, you find lambda 2 and a2. It's not so easy because these numbers in general are complex numbers. And so when you do it numerically, you have oscillatory functions, cosines and sines. It's very hard to recognize numerically. And that's what I was going to explain, how you find them anyway. But you can find these numbers. In the case of the Dedekind eta function, the AI will essentially just be the partitions of n, because the function is just invariant under this thing. But here there are some crazy numbers which behave in some very, very strange ways. So it's a sum of pure exponentials. So maybe I should have maybe called it e to the minus lambda t, and then lambda goes to infinity. So it's again the sum ai e to the minus lambda it. I mean, there may be a finite number of negative lambdas, and also they're complex numbers. But their real part, at least, will go rapidly to infinity. And there's a closed formula for all of this, finally. But the surprise when I did this already for s equals 2, I found these numbers successively by taking very large t. Computing this is very, for eta 2, the corresponding thing. So if it's eta 2, it would also be true with squared this dt inverse. You find the first one, then you find the second, then you find the third. After you found 20 of them, you can guess the pattern. But for some of the others, if kappa was not 0, sometimes you need hundreds of terms. Doing this numerics hundreds of times on the computer before I could guess the pattern, because it was quite complicated. But once you have this, you have an asymptotic expansion. But in principle, you're only finding each exponential term. There might still be an error, which was yet much smaller. But when you find them, then if you check on the computer the actual sum, which is convergent, it actually converges to this. And that is this theorem in the simplest case. But there are much more complicated theorems, which aren't for minus 1 over tau, but are when you apply any modular transformation. So I can just say if I apply any, for any eta s, if I apply the modular transformation law, then there's some similar but much, much more complicated function. So this is a nice aspect. And now I come to the last part. The reason that Hardy and Ramanujan did their thing, of course, was to get the asymptotic formulas like the one I showed here. So for that, they introduced the circle method. So remember that P of Q, which was Q to the 1/24th divided by eta of tau, so it's essentially modular. So this was the sum P of n q to the n. So by Cauchy's theorem, we know that P of Q, that P of small p of n is exactly 1 over 2 pi I times the integral over a circle. Let's say Q is R for any R less than 1. So you integrate over a circle inside the unit disk, and then you just take capital P of Q which is the same as h of 2 pi I tau dq over q to the n plus 1. And so what they do is they take r very, very close to the unit circle, and they look, what is the behavior of this function eta near this point? And this point, as I said, when q is 1, that corresponds to tau is 0. And by inversion, that corresponds to tau goes to infinity, where we know everything. So we know how the function looks here. But similarly, we know how it looks here, but it's a different element of SL2Z. So it's got a different transformation law, different asymptotics, and it's much smaller. And similarly, we know what it does near the cube, the third primitive unity, and it's eta 3 inverse. And here you have I, which is eta 4, and minus I, and so on. So at each fixed root of unity, you know the exact asymptotic size. And this exact asymptotic size, this will grow exponentially in log r. This will also grow exponentially, but the exponent will be half as big. This will be a third as big, a quarter. And so when you do the integral, that's the circle method, you do the integral, you get a contribution from the points in the neighborhood of each of these rational numbers. So you find this is roughly so I write every rational number as a over k, and then you'll get the contribution of the arc, of the part of the circle near a over k. And then that contribution for k equals 1, there's only one for k equals 1. That's exactly this first term. If k is 2, then a is 1, and so you have you'll have an e to the 2 pi I n times half, so it's minus 1 to the n, but you'll have a smaller one, and a smaller one, and so on. So that's how the method worked, but the actual computations, as you can imagine, are quite complicated, since the answer is quite complicated. So now we do the same thing here, but we can't use this transformation law because there isn't one. Instead, we use this thing. So as I said, there is a theorem for eta 2 of any modular transformation in terms of this eta 1 over s at some other points. So if you use that, so using this expansion that eta s of any a tau plus b over c tau plus d is some product of eta 1 over s of something, and this thing is a function of tau itself. So, I mean, it's a power of tau. Remember, z to the s is plus or minus tau, so z to the 2s is tau squared. So as tau goes to infinity, z goes to infinity. So these are completely known. This is a known expansion. And so we know the size of this we know what this function looks like near q is equal to e to the 2 pi I kappa for any rational number kappa, because as I already said, any number kappa you can write as a over c, complete to a matrix. And so as tau goes to infinity, this tells you what's happening. So that gives you the individual contributions. And so you get an explicit formula, which I won't write down, similar to this. It's an infinite sum, but there's something very different. Here, for Hardy and Ramanujan, so the number of terms for each k, there are 5 k terms. I think most people know number theory. Certainly know it's the number of integers modulo k prime to k. So all 5k values of a for given k, for fixed k, of a modulo k, so it's periodic, so it's only modulo k, give contributions of the same order. And that order is what I already told you. I'll leave out the prefactor, but it's the square root of pi square root of 2n over 3. So contributions to p of n. Usual partitions. You simply remember in these terms, the first term was the exponential function pi square root of 2/3 n minus the 24th. The second term, it was the argument was 1/2, then 1/3. So for each k, you get this, but they all have the same order of magnitude, and so you get some periodic function. But everything's very easy. The first term has 1,000 digits, the second is 500, 333, and so on. But here it's completely different. Each of these contributions, I can give the asymptotics, but it's exponentially big, but the exponents do not only depend on k, they depend on k and a. And the actual formula for that is a complicated combination of, for instance, dilogarithms in the case of S is 2. So it's not even an elementary function, but you can compute it for each k. And so when you do that, you find something very surprising. So I don't know anymore where to write it. I should keep an eye on the time. The time is essentially over. We started, I think, a few minutes late because we were waiting for Nikolai, so I'll take another minute or two. So what did I want to say here? So for Hardy and Ramanujan, k equals 1 gave the biggest term. K equals 2 is much smaller, and it's roughly the square root of the main term. K equals 3, whichever a could be 1 or 2, it doesn't matter. It's again much smaller. It's like the cube root of the main term, etc. So they come in decreasing order. But for s equals 2 or higher ones, I only did s equals 2. It's not like that. K equals 1 is still the biggest. But then k equals 4 is the next biggest, next most important. And then I have written down what the actual order was. So they come in some completely bizarre order that I don't even see where I wrote it down. Yeah, it's 1, 4, then it's 2, which you would expect, but then it's not 3. The next one is 8, then it's 16, and now finally k equals 3, k equals 25. But it's even worse than that. Not only are the different k's not in the natural order, but as I said, for each k and each a, you get a contribution. A and minus a give the same, but different a's give different things. So some of the terms with k equals 16 are bigger than these, but some are much smaller. So you get a very, very mixed up thing, a sum of exponential terms. Each one you can write down. It's an infinite sum, and they get smaller and smaller, but it doesn't give you, it's not as nice as Hardy and Ramanujan, they don't come in order. And the other thing is I tried quite hard. I could not get nearly as good an approximation as they did. So their approximation, I told you, is so good that the error is actually smaller than 1. It actually tends to 0. I couldn't get that. So in the typical case that I did, I looked at, and then I'll stop. I looked at the number P2 of 100,000, which was, I have the numbers all written down here. It was, I think, around 10 to the 59. And then the main term, of course, was the same. So that was 10 to the 59. This contribution was, I think, around 10 to the 23, so much smaller. But then they jumped up and down. But no matter how many terms I took, I could not get closer than, I was off, I think, still 10 to the 6th. That's pretty good because you start with 10 to the 60. So at least you have the first 55 digits correct. But I couldn't get down to a good error, so there's still an interesting research problem left to do. And there are many, many more questions, I think, about this. So I'll finish with that. So.
A wonderful talk. Any question?
Somebody must have a question. No, a few people do. Yeah.
Okay, I will ask a question. Actually, in the case, the first power case is just the Poisson summation, right?
So the original case, yeah.
Yeah. And then for the square case, can we still derive this function equation from certain function equations? Or
First, I can't hear you well. I'm not understanding. Can I derive which functional equation?
The square case.
Wait, do you mean this transformation equation?
Eta-2 case, for example.
Well, I mean, there are maybe 20 different known proofs. It's a very well-known theorem, and there are many proofs. Zagier gave a beautiful proof. So there are many ways to prove this.
Okay. But then, I mean, in
general. But I can also do, this one, so the new theorem for eta2 and eta3 and so on. I mean, there's also a proof, but there's just one proof. I mean, it's a theorem, so there is a proof. But I didn't understand your question.
No, I want to know whether it's related, for example, to the Poisson summation, certain kind of Poisson summation or not.
I'm not catching the words. Can you speak more clearly? I didn't catch.
I mean, can we always turn this into a certain proving certain Poisson summation?
It has nothing to do with Poisson summation. That doesn't work at all here.
Okay.
So, but even for the Dedekind eta function, maybe I guess there are proofs of Poisson summation, but it's not the right method. So the beginning is something which is weaker. It's less precise than Poisson summation, but it's much more general. That's the Euler-Maclaurin summation formula. So Poisson summation, if you have a nice function, say small at infinity and smooth, and you want to know the sum f of n over all integers, or more generally f of x plus n, all translates by integers of a point. There's a nice formula for that, Poisson summation, which is that it's the corresponding sum of the Laplace of the Fourier transform. And in particular, if the function is very small, there's one leading term which comes from the constant term. Euler-Maclaurin is weaker because it's not as precise a formula, but it's much more general because it's the sum over half a lattice. It tells you if you sum f of n for n from 0 to infinity. It gives you a beautiful formula for that. Of course, if you know how to sum over all positive integers, you also know how to sum over all negative integers by changing the sign. And then you can add them and you get the sum over all integers. So Euler-Maclaurin gives you a weak form of Poisson. Poisson is much stronger. But Poisson is only for the whole sum. But here, this product, so the first step in doing any analysis of this, now I lost the chalk here. So since PS is given by a product, so that means that the log of PS is given by the sum, n from 1 to infinity, and then the log of this is the log k from 1 to infinity, 1 over k, q to the power k, n to the s. So of course the leading term, but here you have no sums over the whole lattice. You have sums of only a half lattice, k positive, n positive. So when you try to understand this, indeed the first step is to use Euler-Maclaurin to get the asymptotics. And that's what I did to get this to all orders. But then after you have it to all orders, that only shows that the ratio of the left and the right-hand side is extremely close to 1, more than exponentially close. But there could still be an error. But it turns out that I was surprised. That's what I expected. But when I computed on the computer, the two sides were exactly equal. They weren't just us. I mean, I could take a tau which was not going to infinity. Tau was, 1/2 plus 3 times I, or something like that, and compute both infinite products with 1,000 decimals, and they were exactly equal, and then find that to prove. So you cannot use Euler-Maclaurin, and you cannot use Poisson. You have to do, it's standard analytic tricks, but it's not straightforward, and you can't generalize at least I couldn't generalize any of the usual proofs for eta that I know. Okay. So I don't know if that answered the question.
Thank you.
Thanks. Thank you for the great talk. Maybe I just have a small issue. Maybe it's a typo. For the definition of eta2 tau, I didn't.
Where am I? Here?
No, the eta2 tau up. Yeah, up. The expansion you write 1 minus q, 1 minus q fourth, 1 minus q. Because it looks like there should be a term of q to the -1/2 zeta -1, which is non-zero.
No, because this is eta2. I wrote that. The definition of P, so PS of Q, the original one is the generating function, it's just these. Yeah. But the eta function is 1/2 zeta of 1 minus S.
Yeah, 1 minus S.
Yeah,
S
so if S is 2, oh, sorry.
Yeah, it's not
right.
Zero, right?
You're right, it's a typo. Thank you.
Oh.
Now you've made me very worried. The paper is published. Let me check whether the typo is also in the paper. That would be embarrassing. But I'm happy to say that in the paper, there's not a typo. By the way, you made a mistake. This is not a typo. It's a word I invented. This was a choco, because I'm not typing. So thank you very much. You're 100% right. you're doubly right. First, it should be that a priori, and secondly, it wouldn't give the right value for s as -1. So indeed, it's minus s. Thank you very much. So for the original case, z of -1, that part I wrote correctly. I think it's gone now. Z of -1 is minus a 12th, and so minus a half of that is 1/24. But indeed, it's minus. This is a general rule in all of mathematics. I can say this for, especially for younger people who maybe don't know this principle. If you have a sum over n greater than or equal to 0, then many times of something, you should take the modified sum. I'll put a half. So let's call this an. The modified sum means that the first term should be counted a half. So very often when you truncate a sum somewhere, and more generally, if you sum n from I to j, you should really go from I to j to count both endpoints with multiplicity half. Because if you have two intervals, you sum from I to j and j to k, then you'll get the point at j twice. But you don't want that. You want it to add. Like when you integrate from a to b plus integral from b to c, it's the integral from a to c. So when you sum, you should very often count the n terms with a half. And therefore, it's exactly the same principle here. We should have, so if you write this and then look at what you're doing, you'll find that you should exactly have the Riemann zeta function, but with a factor half. And so it should be minus a half zeta, but indeed it's minus s. So thank you very much. That's very sharp looking at the board and thinking. I'm really impressed. But at least in my published paper, I wrote the right thing. Anyone else?
Any other question?
Professor, can I ask question?
Go ahead.
Can I ask question?
Of course.
Whether there is exact formula of cube square of partition and how to compute it?
So I couldn't, first of all, who's speaking? It's somebody over line. So who is it? Is the name visible?
No, we have to check the computer.
Oh, who are you? But I didn't hear the question.
Online.
Yes, but even
audience.
online, you're somebody. You have a name. But
My
did
name
somebody
is
catch the question? I wasn't listening because I was looking for where the voice came from. Did anyone hear the question, or could you please repeat?
Could you please repeat?
It's Huazhong, but and I'm a hobby of mathematical. So I want to ask a question.
A hobbyist, but I still didn't get a question.
I don't get it. Sorry.
I ask a question is whether there is exact formula of cube square of partition n and how to compute it.
The formula for partitions of n?
Yeah, I think he's asking the exact formula.
Into
My
squares.
question is
Well,
whether
there's-
there is exact formula of cube square of partition n and how to compute it. Can you
I'm
hear?
still not getting the question. How to compute eta?
Maybe you can type it. Since
No, I didn't.
A question is whether is the exact formula of cube square of partition n.
Hills square.
Hilbert?
Do you know what that is?
Cube square of partition n. Cube is cube square 就是cube for example n write as one cube plus two square like this.
No, but that doesn't make sense. If you fix the number, like the number of ways to write n is the sum of two cubes, already there's no formula for that, but it makes sense. But here it's a partition. We have many terms.
Yes.
It's not 2 squares or 3 squares. It's an arbitrary number of squares, but with no repetitions and up to orders. So if you say I mix squares and cubes, then it's not one number because you can have a certain number of squares and a certain number of cubes. It's not a natural question. If you fix, like writing n as a sum of two squares or two cubes, there's a huge literature. I've worked a lot on sums of two cubes. It's a beautiful question. And also on other things, there's Waring's problem, but that's a fixed number, like two terms, or k, like 9 cubes. That's a famous problem of Waring, but you cannot change the number. But partitions is not the same. It's not a Diophantine equation because it is an unknown number of variables. It's n1 squared plus n2 squared up to nk squared, and we don't know how big k is. It's everything. So it's not a Diophantine equation. It's not points on a variety. It's somehow points on. Anyway, it's not Diophantine. So I think I cannot make that question into something that one can reasonably expect an answer. At least I don't expect an answer.
Thank you very much.
Okay, if there's no more question, let's thank Professor Zagier for talk again.